So we were into, if you just check, we were into getting the temperature distribution of a plane wall. So we did get mathematically the temperature distribution of a plane wall of this form, and only one term series is enough for us, we said, if the Fourier number is greater than 0.2, and these were the temperature distributions. If you really look the plane wall, which I had consciously not shown you thus far, is this. So you can see that here this is Ti and this is T infinity. So as this is T equal to time t equal to 0, as T goes on increasing, eventually at T tending to T infinity, T time tending to infinity, the temperature reaches T infinity, the plane wall temperature reaches T infinity. But in the meantime, the temperature distribution, you can see that it is symmetric, number one, and the center line temperature is higher compared to the temperature at the wall, because at the wall the heat is removed, so naturally the temperature will be lower here. But eventually the temperature will, even at the center, also reduces to T infinity. So, but there is some time till T equal to T2, for example, here this is T equal to 0, this is T equal to 1, T1, and this is T equal to T2. The center line temperature continues to be at Ti. So till T equal to T2, the center line temperature has not changed or has not felt the heat taken away by this fluid. The heat is not taken away. So this is an important point to note, and this is how the temperature distribution looks like when you plot taking that exponential and other functions together in a plane wall. Okay. So now only one issue before we go to the semi-infinite thing which I want to cover is that the Biot number infinite. So I just touchingly told that the Biot number infinity means, what does it mean? So if you just take up Biot number is infinite means, so let us say Biot number is infinite. What is Biot number? HL by K. So it tends to infinity implies, what does it imply? It implies that the H is very high, then only this is possible for a given plane wall and a material of given thickness. So when can one achieve very high H? This is possible in case of boiling or condensation, where the heat transfer coefficients can be of the order of 50,000 to 1 lakh watt per meter squared Kelvin. In that case, what happens is that the 1 by Biot number, in that case you just see 1 by Biot number, that is K by HL is 0. That means if you have H very high, H is infinite, then the T infinity is equal to the T wall, because there is no convective resistance. 1 by HA is the convective resistance. Convective resistance is 1 by HA. If you recall, in 1D conduction we said 1 by HA is convective resistance. If H is very large, that means this convective resistance is 0. That implies that T infinity equal to T wall. That means for a Biot number tending to infinity case, I have actually solved for constant wall temperature case also. That means if you were having a plane wall and which is sitting at a temperature T equal to Ts, T equal to Ts, and now you want to get the temperature distribution inside, then you can get taking the Biot number as infinity. So, you have not only solved the temperature distribution for convective boundary condition, convective heat transfer boundary condition, which we did in the previous classes, you have also solved for constant wall temperature. So, only thing, the procedure is all same for constant wall temperature case. Only thing is that you have to solve, you have to take the lambda 1 and A1 for Biot number corresponding to infinity case and solve the rest of the problem as same. So, that is about the constant wall temperature case, which we could fortuitously get from the convective boundary condition itself. So, with this we can move on to what is called as semi-infinite medium or transient heat conduction. Transient heat conduction in semi-infinite solids. So, what do I mean by semi-infinite solids? Instead of telling it mathematically, let me explain you this through example. Let me explain this through an example. Let us say I am sitting in Kashmir and I have my pipe wall. This is my pipe in which the water is flowing. Okay? And this pipe is put in soil. This is dug, the soil is dug and the pipe is laid out. So, the pipe is put in the submerged soil. So, now the initial temperature is 15 degree Celsius, let us say. Now, this is what it is, but all of a sudden it starts snowing. It starts snowing, because of which the surface temperature, becomes minus 10 degrees Celsius. But now what happens? Now this is okay. So then what is semi-infinite about this? Now if I take, how do I model this? Dou squared T by dou x squared equal to 1 by alpha dou T by dou T. This is what we get. Now I know the initial condition T x comma 0 for a plane wall. If I take this as a plane wall, this is Ti. This is initial condition. Okay. Now T at 0 comma T, that is at the surface, that is, this is my x starting, that is x equal to 0, it is Ts. This is one of the boundary condition. This is the snow temperature, let us say. But now if x is very lower than, I have dug very deep, this x is very large, several tens of meters I have dug, then my temperature at any time t or for certain time t, it is going to be at Ti. It won't be any different. Under these circumstances, I can consider this as semi-infinite. That is, it's a this is called semi-infinite situation. I will elaborate this still better through various examples after we have solved this. But for now, this is the physical situation where I have put a pipe in Kashmir below the soil and the snow has taken over, so that the surface temperature is minus 10. But I have laid down my pipe so deep down that my pipe will not feel the temperature variation caused because of my snow, or the heat transfer it does not feel, or how deep I should dig, how deep we need to dig so that my water inside the pipe does not get frozen. That is the practical solution. My contractor is asking me this question, sir, how deep I should dig so that for 6 months or for 3 months in the winter season my water continues to be remaining as water while it is flowing, otherwise it will freeze down. So, to solve that, this is the problem I have to solve. This is going to be little different from what we solved earlier, that is the plane wall problem. How it is going to be mathematically different, and what is the simple solution what I can get instead of the complicated solution what we got for the plane wall, we can check that using the semi-infinite medium. So, this is what is the semi-infinite medium. So, now let us get how do I solve this problem of semi-infinite medium, that is dou squared t by dou x squared equal to 1 by alpha dou t by dou t. You know that this is partial differential equation. Now, I can transform this partial differential equation into ordinary differential equation by using a transforming variable. I will explain that transforming, how I take the transforming variable little later through physics, but for now you please take my words and take this transforming variable as eta equal to square root of x by square root of 4 alpha t. X is the space, alpha is thermal diffusivity, t is the time. So, now let us do this transforming of partial differential equation to ordinary differential equation. So, how do I do that? So, dou t by dou t is equal to, if I can write this as dt by d eta into dou eta by dou t. Okay. So, dt by d eta retain as it is, dou eta by dou t, if you differentiate this with respect to t, x by square root of 4 alpha are constant, t to the power of minus half will be minus half nx to the power of n minus 1 minus half minus 1. So, that is equal to dou t by dou t is equal to dt by d eta into, that is negative sign, into negative sign x divided by 2t into square root of 4 alpha t. It is t to the power of 3 by 2 minus 3 by 2, 1 I have put inside the square root and 1 is outside. So, this is dou t by dou t. Now, let us take up dou t by dou x, because I need dou squared t by dou x squared. So, first let me get dou t by dou x. Dou t by dou x is nothing but dt by d eta into d eta by dou eta by dou x. That is dt by d eta into dou eta by dou x, that is it is differentiating with respect to x. So, that is it is nothing but 1 by 4 alpha, differentiation of x with x will be 1. So, you got this as this. Now, similarly dou square t by dou x squared will be equal to d squared, if you again differentiate this you get d squared t by d eta squared into 1 by square root of 4 alpha t into 1 by square root of 4 alpha t. You have to differentiate again twice. So, you get 1 by 4 alpha t into d squared t by d eta squared. Okay. So, now let us substitute this dou squared t by dou x squared, these two terms into this equation. So, if I substitute that, so I get 1 by 4 alpha t into dou squared t by dou eta squared is equal to 1 by alpha into minus x divided by 2t into square root of 4 alpha t into dt by d eta. So, this is d squared t divided by d eta squared. Now why it is, you will realize why it becomes ordinary differential equation in a second, you will realize. Now alpha gets cancelled, t gets cancelled. Now what will I get? D squared t divided by d eta squared equal to minus 2x divided by square root of 4 alpha t into dt by d8. Now if you recall, what is eta? Eta is x by 4 alpha t. So this is nothing but eta. So I get d squared t divided by d eta squared is equal to minus 2 eta dt by d eta. Okay. So now you can see that my temperature is only a function of eta, but here my temperature was a function of both x and t. So that is why PD, that's why it was PDE here, now it is ODE, because my temperature is only a function of one variable, that is eta. But that magic was done through eta. How I chosen this x by square root of 4 alpha t, I have not explained, you will have to wait for that. I will explain little later. Okay. But now let us convert the initial conditions also into eta terms, that is t of x comma 0 is equal to ti. This is the boundary initial condition. At t equal to 0, what happens to my eta? Eta equal to x divided by square root of 4 alpha t. That means at t equal to 0, eta tends to infinity. So at eta tending to infinity, t at eta tending to infinity, t becomes ti. This is one initial condition. Now let us take up the boundary condition, that is t at 0 comma t is equal to ts. That is at x equal to 0, eta equal to x by square root of 4 alpha t, eta is also equal to 0 because x is 0. So that means t at eta equal to 0 is ts. There is one more boundary condition, t at x tending to infinity at any time t is equal to ti. That is the speciality of semi-infinite medium. That is, as x tends to infinity, eta tends to infinity. That is, t of eta tending to infinity is equal to ti, which is what we got even for the initial condition here. So that means you need only two boundary conditions because it is second order equation. So you have two boundary conditions, that is equation is d squared t by d eta squared equal to minus 2 eta dt by d eta, and t at eta tending to infinity is ti, and t at eta equal to 0 is ts. So this is what we need to solve now. So let us see how do we solve this equation. Now it is simple separation of variables, actually we can do this. So what we will do is d squared t by, so let me get started in a fresh page, d squared t divided by d eta squared is equal to minus 2 eta dt by d eta. Okay. Now I can write this as, this implies as d by d eta of dt by d eta is equal to minus 2 eta dt by d eta. Let dt by d eta be p. So if that is the case, I get dp by d eta is equal to minus 2 eta p. So I can do this by separation of variables, that is dp by p is equal to minus 2 eta d eta, minus 2 eta d eta. Now I can integrate it. I have separated by variables. Now integrating, if you integrate, you get log p equal to minus 2 eta squared by 2 plus c, or dt by d eta, p is nothing but dt by d eta, this is dt by d eta. So dt by d eta equal to c1 e to the power of minus eta squared. I have subsumed, c has become c1 now, and 2 gets cancelled out. So dt by d eta is c1 e to the power of minus p squared. Now again, if I integrate this, I get t equal to, integrating again with respect to eta, t equal to, I get c1 integral of e to the power of minus eta squared d eta between the limits 0 to eta plus c2. So there are two constants and I have two boundary conditions which I have been given, that is t at eta equal to 0 is Ts and t at eta tending to infinity is Ti. Now t at eta equal to 0 is Ts. So what will happen if I substitute this here? That is, you get Ts equal to c1 e to the power of minus 0 d eta 0 to eta plus c2, this is 0. So c2 will become equal to what is called Ts. Now if I substitute this, so you get t equal to c1 integral of 0 to eta e to the power of minus eta squared d eta plus Ts. Okay. Now we need to find c1. So that is Ti equal to c1 integral of 0 to eta e to the power of minus eta squared d eta, sorry, this is t, okay, plus Ts. Now we have another boundary condition, t at eta tending to infinity, that is equal to Ti. So Ti equal to c1 0 to infinity e to the power of minus eta squared d eta plus Ts. Incidentally, this is what is called as error function. We have defined what is called as error function. I will show you little while from now what is error function. Error function is, if you have error function of z equal to, it is given by 2 by root pi integral of 0 to z e to the power of minus t squared dt. So what is this error function? This error function, if you have error function of z, can I calculate error function in terms of series? Yes. Error function of z is 2 by square root of pi into z minus z cube by 3 plus z to the power of 5 by 10 minus z to the power of 7 by 42 plus z to the power of 9 divided by 216, so on and so forth. If I have to show you the graph, how does it, the figure, how does it look like? So this is how the error function looks like. So the error function definition is encountered in integrating normal distribution curves by the Gaussian distribution. So error function z is 2 by square root of pi 0 to z e to the power of minus t squared dt. If you plot that, this is how it looks. This is error function and this is z. So this is the series function. So what is interesting here is that error function of 0, you can see that it is 0, and error function of infinity is 1. error function of infinity is 1, and it's an odd function, that means error function of minus z is equal to minus of error function of z. So error function, so let us write few conclusions of error function, that is error function of 0 is 0, you can see that here is 0, and error function of infinity is 1, and error function of minus z is equal to error function of minus of error function of z, okay, that is, and also error function of z plus error function complementary error function of z is equal to 1. So what is this? This is what is called as complementary error function. We are going to use this little later, so that is why I am putting all of this. So to imagine error function is just a series equation like this. Now let us get back and get our C1. So if you get that C1, so you get Ti equal to, this is the error function. So if it is infinity, so what do I get? This is C1 into, so the error function is this. So this becomes the error function. So I can write e to the power of this becomes error function of, that is, you get this as 0 to infinity C1 0 to infinity e to the power of minus, sorry, let me write in one shot, C1 equal to Ti minus Ts divided by 0 to infinity e to the power of minus eta squared d eta. Now this being equal to 1 for infinity, so this error function of infinity is equal to 1, that means that is equal to 2 by square root of pi integral of 0 to z e to the power of minus t squared dt. So this becomes equal to square root of pi by 2. So that is Ti by Ts divided by square root of pi by 2. So that is C1 equal to 2 into Ti minus Ts divided by square root of pi. Okay. So we got C1, so we got C2. So now we have gotten the temperature distribution. If I substitute that here, I can get the temperature distribution. So my temperature distribution is T equal to C1 integral of 0 to eta e to the power of minus eta squared d eta plus C2. So C2 is Ts and C1 is 2 into Ti minus Ts divided by square root of pi. So T equal to 2 into Ti minus Ts divided by square root of pi into 0 to eta e to the power of minus eta square d eta plus Ts. So T minus of temperature at any time T minus Ts divided by Ti minus Ts, sorry, temperature at any eta, this is equal to 2 in 2 by square root of pi. This is nothing but error function. Whole of this is 0 to eta, sorry, e to the power of minus eta square d eta. This is nothing but error function of eta. So T minus T of eta minus Ts divided by Ti minus Ts is nothing but error function of eta. So if I know the T, I know Ti, I know Ts, at any eta I need to get the T by getting the error function. How do I get the error function? Actually it is calculated and tabulated. The error function is calculated using this function, but you do not have to calculate every time. It is calculated and kept. So if this is your eta, the error function of eta is calculated and kept. So that's about the temperature distribution. In the next class, I am going to teach you about the surface heat flux and also how at other boundary conditions. So we are solving it for constant temperature, surface temperature. What will be the solution for constant heat flux and surface convection will be covered in the next class, and also we will solve this problem. And another question which is pending is how on earth I came to know that eta equal to x by square root of 4 alpha t. So these two questions I will be addressing them in the next class. Thank you.